The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so this is the first true review session in 18085. The last Wednesday, the first Wednesday afternoon, was a brief review of topics in linear algebra. But now we're into the course. We've done 4 lectures on the first 4 sections of the textbook, and 1 homework problem in and back, and a second homework set for next Monday. So I'm ready for any questions, including questions that are on the homework if necessary, but anything at all. Or maybe I'll just ask whether the pace, so this is really informal, is the pace of the course, now today's lecture had a lot in it, as I realized when I saw that the board was still full of 18085. And there was a little more still to do because we didn't finish the matrix part. But are you okay with the sort of speed of the course? So that'll be one question. And then what about specifics? Somebody start off, if you will. Anybody? Yeah, thanks.
Well, I actually had a question about the lecture earlier today.
Okay, go ahead.
I was just going to look it up in the text. But
that's all right.
I haven't had a chance to. But
yeah.
Okay, so I'm not really sure how you take the initial conditions and apply them to the ramp function to actually get a solution.
Yeah. So the question was, so that's what luckily happens to be still here on the board, right? Yeah. We've got these boundary, I would call them boundary conditions. So this is definitely, we're in a part of math that's about boundary value problems more than time isn't in the picture. Yeah, I mean, later time will get into the picture. With this particular example, the general solution is a standard ramp at the point A, where things are happening, plus the c plus dx, the usual. So that's a particular solution. That particular solution has the right behavior at the impulse. It has, by the right behavior, I mean that the second derivative of the ramp is a delta. And when I put the ramp at A, then the delta will show up at A. And when I put on that minus sign, it'll mean that the second derivative is minus the delta. So the slope will step down. So that's a particular solution. But that by itself, what boundary conditions, what does that equal at 0? And what does that equal at 1? If you remember the ramp. So let me just draw that ramp again. So the ramp was really based on centered at the point A, and I'll put it with the minus sign. So it came along there and down there. And now suppose this is one end of our interval, and that's the other end. Okay? So is that ramp the answer to our problem? No. Well, it happens to satisfy this boundary condition. Happens to start out at 0. But it doesn't end up at 0. So just like every particular solution, we need a little more. We have to include more solutions, because that was only one. All those are equally good solutions. If I add c plus dx, the second derivative of that is 0. So it doesn't spoil anything at all. On the contrary, it adds more solutions. I mean, the great thing we're using here is that our equations are linear, and when 0 is on the right-hand side, notice there's no arbitrary constant. I'm not putting an arbitrary constant on that particular solution. It's one particular solution plus a subspace, if I use that language, a lot of solutions to all the solutions to the problem with 0 on the right-hand side. And these are the solutions, these are the null space guys, the ones that have 0 on the right-hand side. Okay, now we need those, and the effect of those will be to move that ramp, and effectively what are they going to do? They're going to swing that ramp around. It'll stay a ramp, but instead of being level here, it'll go up. And instead of going down there, it'll go down there. It'll be the same ramp with still that slope dropped by 1. Slope went down by -1. And that's not going to change here. The slope will still here go down by -1. But now I've just adjusted it so that it goes through it satisfies the boundary conditions. And in the second problem with the free end, again, here's my ramp. But now I'm going to adjust it. And what happened? It just needed adjustment upwards. Because this was the 0, this was the u equals 0 fixed guy. And now if I'm doing u prime equals 0, the free guy, I can lift the whole thing up. So you see, I just lifted it up to the point where it came out right there. So in this case, I just needed a c. And in this case, I just needed a dx. And in other cases, I might have needed both, a little bit of c and a little of dx. Anyway, that's the what was, maybe that's sort of repeating what we did today a little bit. But mechanically, it's just we've got a particular solution, and we've got the complete solution, and then we just have to choose C and D, and we've got 2 conditions to do it with, the 2 boundary conditions. Could have other boundary conditions. Now, what about I guess what will often happen in these review sessions is I get on a roll, and I just carry on with it. You know, you start me with a question, and I can't stop. Right. So I'll go a little longer, but then I will stop, ready for the next one. What about? So we haven't discussed the free. U of 0, u prime. Sorry, free is u prime. That's free at the left and free at the right. Okay. What's up with that? What's the solution to that? Again, I'm looking for minus u double prime equal an impulse. Okay, with those 2 boundary conditions, free. And do you know what's going to happen? No solution. No solution. Now, it'd be interesting to see why not. Why no solution? Well, one way to do it is try. Other right-hand sides could have a solution. So it's not just that there's something the matter here. Specifically, that right-hand side, and most right-hand sides will fail. But let's just see it with this one. Why does that fail? Well, you can see. I can't. Yeah. The slope here is 0, and the slope here is -1. If I adjust those, I can't get, this is asking me to get slope 0 at both ends. Can't do that, right? I can't, it's just not possible for me to know this will add a straight line, but it's the same straight. I can't get a ramp that comes flat at both ends, because once I say what it's doing at the ends, I've got it. And you see what I mean? That to get, I'm looking for one that starts flat and ends flat, and that's not in my family of solutions. That problem just doesn't have a solution. And so that's one way to do it, is look at the solutions and realize you can't satisfy both boundary conditions. Another way might be this. Yeah, this is a little bit deeper way, and it leads to something better. Suppose I take the integral. So this is an equation that's supposed to hold. Let me integrate both sides from 0 to 1. So there's the idea I'm putting in now. To go a little further, to discover when this has a solution. Or let me take more generally, minus u double prime equals some f of x. So some other load, not necessarily a point load, not necessarily a uniform load, but maybe some other load. And now my boundary conditions, I'm trying to do free. And usually, no solution. But let's just see why and when there might be a solution. The key idea is integrate from 0 to 1. Okay, what do I get on the right-hand side? Well, I get the integral of f, whatever it is, and I would call that the total load. Fair enough? The total load of, if it was a delta function, the total load would be 1, and it would be all in one spot. If it was uniformly over the whole interval, well, I guess that would also integrate to 1. So the total load would be 1 spread out. But it could be a mixture of the two, could be a few delta functions, whatever. What happens when I integrate the left side from 0 to 1? Can you do that one? The integral from 0 to 1, there's dopey minus sign, u double prime dx. What does that, what do I get? Why do I say that's a good idea? If I integrate the second derivative, I get the first derivative. The integral of the second derivative will be the first derivative with the minus. So it's minus the first derivative. And what do I do now? I plug in the endpoints, right? Integrate. I'm integrating 0 to 1. So I found the integral. I put 0 to 1 in there. So I get, so what is that? That's minus the derivative at 1 plus the derivative at 0. Okay. And now what's that? That's 0. By my boundary conditions, that's 0. So what have I found? I've found that if these are the boundary conditions, then when I integrate the left side, it's going to give me 0. So what loads could be okay? What loads f of x could allow me to solve this equation? The condition will be, what do I need for the total load to be able to solve this equation? The integral of the left side was 0. So the integral of the right side had better be 0. Okay, so that's the condition. For if I have these boundary conditions, then my problem is singular, usually no solution. It's like having a singular matrix. It's like having this particular singular matrix, of course. Whoops, not that one. Let me get the plus sign in the right position. Yeah, sorry, that's a plus. Minus 1, minus 1, 2, minus 1, minus 1, 1, right? This is the discrete version with a 0 slope at both ends. It's our T matrix. No, what matrix is it? B. It's our B matrix, both ends. Okay. So I'll just come back here and then I'll do the discrete one. So tell me a load that we could handle. A load we could handle. So the integral has to be 0. So suppose my load has a delta function at A. Well, that integral is 1. So can you fix that to change that load or do something, maybe put on another load to get a total load of 0? Well, what shall I do? Add another guy. with a minus sign. In other words, maybe this, a delta function at some other point B. Well, that would do it, right? I believe we could solve that problem, even with these bad boundary conditions. We could solve that problem because the total load would be 1 from that minus 1 from that. The total load would be 0. You could, in other words, what would our solution look like? It has to start with 0 slope, so it would buzz along to A, and then after B, and what does it have to do here? Yeah, if I graph the solution to this guy from 0 to 1, it starts with, it's free, so nothing's happening until I get to A. Then what has to happen? It's got to, let's see, if I'm graphing U, it'll be a ramp, right? It'll be a ramp, yeah, because I'm 2 derivatives. So, and it has to ramp down by 1, so it'll ramp whatever it does, I don't know where it stops. Where does it? Wait a minute. I haven't practiced these. So I start from the other end.
Yeah, the other end is flat. And then
The other end is flat. What's up? They got to meet here. Oh, the other end is flat, but not at 0. Dumb, stupid. Right, okay. Yes, the other end is flat, right? And it's, oh yeah, look. Oh, wonderful. You see, its slope, that slope dropped by 1, and the slope there increased by 1, back to 0. Slope was 0. It dropped to minus 1 because of that load. Now it increased back to 0 because of this load with the minus sign, and there's a solution. Yeah. So that's a solvable problem. Well, you say, okay, that was a little surprising to get an answer for a singular problem. And no, it can happen. If we have a total load 0, it'll happen. But there is still a but. That's not the only answer. Tell me that picture is a solution, but not the only one. So my point is going to be that when the problem is singular, if there's an answer, you say great, but then something has to go wrong, and what goes wrong is too many answers. So tell me some more, what other graphs would draw solutions to this problem? I could shift, I could lift the whole thing. I mean, yeah, here, I've got a plus C that I haven't used. I could just do the whole thing higher up. Any of these. These would all work. Yeah. So I've got, it's like temperature. I don't have an absolute temperature here. All I've got is, I would have to, it's not determined because there's a plus C that, the plus C satisfied these. The plus C satisfied everything. A plus C, a constant, has 0 slope, it has 0 slope, its second derivative is 0, so it's like unseen by this equation. Yeah. And similarly, can I just make the analogy as I always like to do with discrete stuff? So suppose tell me a right-hand side that we think would probably, is this going to be the same story for this guy? Yes. If I add those, that's like where I integrated there. Here I would add, and I get 0, 0, 0. So this has to add to 0 if there's a solution. So let me put, for example, 0, 1, minus 1. That would be kind of like our delta function in one direction and our delta function in the other. I believe I can solve that problem. So I'm just carrying, because I always want you to see the discrete one as well as the continuous. Continuous involved this integration. The finite one just involves adding. The left side adds to 0, so the right-hand side better add to 0. That right-hand side does. Tell me a solution. Well, let me start out with a 7 there. what's the next guy going to be? Let's see. I want 7. Whatever I put there, I better have a 7 there, right? 7, 7, good. Minus 7 plus 14. Oh, jeez. I didn't know this was going to happen. What? No. No, I want to get the answer 1. Yeah. What was it? What number goes there? 6. Is it 6? Okay, it's 6. Yeah, good. Minus 7, 14, minus 6 is that. And now my claim is that we'll come out right on the third equation. So far, I've just matched the first two. Now, this one gives minus 7 plus 6. That's minus 1. Good. So there's a solution. And I'll leave this problem alone if you tell me the rest other solutions. That 776 was a solution to a singular problem with a right-hand side that had total load 0, so it was okay. But now that's a solution, but there are more. Tell me another one. I can shift it, right? I could make it 17, 17, 16. I could add 10 to everything, right? That's the plus C that I could do over there. Now, that can't change because 17 minus 17 is still 0. Everything minus 17 plus 16 will still be minus 1. All good, yeah. Okay, so that's actually, it just like helps our intuition. And physically, my intuition is this, that I've got this bar, and nothing's holding it. So if I put a weight on it, nothing to hold it, it'll just, rigid motion will take it out of sight. No good. But if I put another equal weight on it, no, it's not a weight. What do I call it? If I lift it at that point, that's the other delta function that's going the other way, then it will sit there, but it would still be in equilibrium if I just moved it up to there or moved it as I like. I don't know if that is kind of a dumb picture, but it's saying what we've said from math. Well, you see where your question led. Yeah, thanks.
Over on the spot that you drew, do you have to have equal area above and below the 0 point? Like since we're integrating it, it has to equal 0?
No, the integral, it was, yeah. Watch what we integrated. We integrated u double prime. So that's not the area. Yeah, yeah. We integrated u double prime and got its integral was u prime. So that just told us that a difference in slopes at the ends. Yeah, yeah. Good, good. Yeah, because our intuition automatically is if we're integrating something, we're finding an area. But here if it was u, then I'd be finding the area under u. But this is we integrated the second derivative. Right. Good. Yes. Anything. Now let's change the subject. Yes, please.
Can you explain why those two numbers in the matrix reflect the boundary conditions?
Yes, I guess so. I'll try. Yeah. Right. And so let's see. So my discrete equation was like minus u. Yeah. So let's back up to the beginning. We've got this minus sign, and we're using a second difference. So second differences have coefficients 1, minus 2, and 1. Okay. Now I'm reversing the signs because of my minus. So I have minus u at some point let's take that as the point to the left. 2 u's at what I'll think of as the center point, minus u, I minus 1, is the load at that center point. That center point is I times delta x. That's where I would be looking. So now I'm using subscript. It's a little bit of practice then to take subscripts, take this way of writing the equation and convert it to a matrix way. It's usually clearer once you see it as a matrix. Okay. Now this is happening at all the points. At I equal at I equal 1, let's say, I have minus U0 plus 2U1 minus U2 is F at, agrees with the load at the first mesh point. That's the center, the point H, delta X. Okay. Okay. And then if I want to back up further, I would have minus U minus 1, but that doesn't really exist, plus 2U0 minus U1 would be should match the load at 0. Okay. So, and so on, forward. But now I want to put in the boundary condition. That's what you want me to do, right? Put in this boundary condition. So what am I going to take as boundary condition? It has to be some approximation to U prime of 0 equals 0. Maybe I'm never going to get to minus 1. Maybe I don't need minus 1. Yeah.
Well, we previously,
yeah? Yeah.
We previously learned that if you do the forward difference for the derivative, then there's an inherent error.
That's right.
Was the center derivative.
Yeah, exactly.
So, but in these examples, it appears as if that's what we chose to do.
We did. That's what we knew about. Forward, we knew about forward difference, so I chose to do it. But then I'd think better of it. Yeah, I chose to do it because it made the point that that at that boundary we were introducing a higher order error, first order error, that's going to wreck things. I mean, it's going to spoil this is second order accuracy, but let me do that first order. So what shall I take? I'm going to approximate that by U. Shall I take this one as I did in class? Okay.
Professor?
Yeah.
Your equation, is that supposed to be minus U, so I plus 1?
Yes.
Or no, sorry, the other one.
Ah, plus 1. Thanks. Plus 1. Right, thanks. Thank you. Good. Okie doke. All right. So, yeah, this is how we got to that equation. If I now bring in this boundary condition, I guess I don't have to, let me take your eye off of that guy for the moment, I think. We're getting beautiful music here. Is it coming out of this box or no? Anyway, okay. Okay, so I'm going to use this boundary condition to say, well, okay, if U1 is U0, I'm going to replace this U0 by U1. Yeah, that's what this is the direct way. I replaced that U0 by U1 in that first equation. And then what I have is minus U1 and 2U1, so that's the 1, and I have the minus U2. So do you see that equation, when I put those together into a 1, is going to, if this is U1, this is U2, this is U3 onwards, that first equation is U1 minus U2, and that's what I've got. This is U1 minus U2. Yeah. So I did it. I got to that matrix. The matrix is actually quite an important matrix, but from the point of view of accuracy in solving this differential equation, it's not the greatest. It's lost accuracy at that point. But the way to recover it turned out to be just a small adjustment at the boundary, so not a problem. Thanks. That's good. Yes, thanks.
What would it mean physically if
Sorry?
What would it mean physically if the boundary conditions were both at the same point?
When the boundary, two boundary conditions at the same point? Ooh, that's a good question. Okay, so when would we have two? So you're instead of a boundary condition at 0 and a boundary condition at 1, you're putting them, is that what you mean? Put both boundary conditions at the end? Yes. Okay, so that would be, that would happen, I would think that would be more, it would be very typical in, let me see if there's some space here. Yeah. That would be very typical, and we will do it. Can I change x to t? Because that's what, if I have some, yeah, what does this problem look like? And u of 0 equals, let's say, 0, and u prime of 0, both at the start, equals 0 or whatever. So what kind of a problem is that? Now these are, I would say, initial values. Initial values. Instead of boundary values, I now have initial values. And can I solve it? Yes. So I'm starting at time 0. This is t equals 0. I'm starting at rest. Nothing, no velocity, actually no displacement, and just going forward in time. So I could solve that differential equation. I'd be interested in the corresponding difference equation. All fine. It's a different category of problem. This is an initial value problem. Like a wave, yeah. So, I mean, it's like tracking some mass that's some satellite. So that's what you're doing in tracking a satellite or a planet or something. Tracking a planet or a satellite, you're solving equations like this forward in time. You know the initial position, and you know the forces acting on it, probably gravity, and you go forward in time. Yes? What would the matrix be? Good question. What would the matrix look like? So this is, okay. So an electrical engineer would call a problem like this, and the kind of matrix that I'm going to write down, I think would be called causal. That word just popped into my head, so let me mention it. You know, part of science and engineering, a big part of it is learning language, learning words. And you have to learn sort of the math language and the engineering language for whatever you're focusing on, but it's good also to know a few other languages. And electrical engineering languages of filters and causal and other things that we'll see are important. What would the matrix look like? Here's what I think it would be. I've made this plus there, just so I'll have to remember that. I think, so I'm looking at U0, U1, no, well, U0 I actually know, so let me start with U1, U2, U3, U4. What would a typical equal sum right side, F1, F2, F3, F4? What do you think, what kind of a matrix am I going to get? Before I put it in there, this is a good question. What's the shape of this matrix? It's going to be triangular. Instead of being symmetric, it's going to be triangular. I'm going to find, let's see, a typical value would be, say, U3, because I've used the plus sign. Oops, I can't make myself do it right. 1 minus 2, 1. That would say U3 minus 2 U2s plus U1 would be the new force. This is the kind of thing we're going to get. 1, maybe 1 something. I don't know what this is. This is up in the in the initial values. But from now on, it'll be below the diagonal. It'll be 1 minus 2, 1. Do you see? We're marching. We're marching forward. We start by knowing these, and then the equation tells us the next one. Then the equation tells us the next one. That's what initial value problems do. You're told how you begin, and you take a step every time, and the new value just needs to know the older values. You see the big difference between that and our problems here. Our problem is looking left and right, looking back and forward. Back for one condition, forward for another. We start with one, but it's more of it's like a hitting problem. We start marching forward in our problems, but we have to hit the other end correctly. We don't know the slope. We don't know the starting slope. We know what we want to hit. Whereas these problems, we're told how we start, and we just follow it in time. Yeah, so that's the difference here. And yeah, sure. Okay.
First, as you wrote that, we have U0, but we also have U1. If we use a forward difference, U1 will be 0.
That's true.
So then that would be part of the
So this will not be, this will be known.
Right.
Yeah, that'll be known. Yeah, U1 will also be known. Yeah, and really, maybe I should have got, let me put even the other known one. Okay, so we know this, so those are sort of not in our, that shouldn't be in our problem somehow.
And my follow-up question is, the final question is, the last row would also indicate a boundary condition. Is this
No, I think, what would we get at the end? No, I don't.
Oh, you get the 1 minus 2.
You're always looking backwards.
Right.
That's the point. Lower triangular matrices are always looking, they only look backwards for earlier values, and then they give you the current value. So that's why lower triangular matrices are so easy to invert. No problem if it's lower triangular, you just march forward. And if it's upper triangular, which way do you march? So if you have an upper triangular problem, suppose I gave you the problem, let me make it upper triangular. So x plus y plus z equals 7, 2y plus 3z equals 12, and z equals 17. So that's upper triangular. Where do we start in solving that one? From the bottom, from the right-hand end, the bottom. And we march backwards in time. And what I was saying about A equal L times U, this is worth seeing. What I was saying about A equal L times U, it was, you remember that? Those letters? What that was saying was that this matrix that's looking both ways can be written as a product of a matrix L that looks behind for old values, and you can go forward with it, and the matrix U, like this one, this upper triangular, 1, 1, 1, zeros below the diagonal, that you go backward with. Somehow that's appealing. It's like aesthetic to break up a two-way problem into a problem that marches one way and then the other. Yeah, and that's, and of course that's what elimination aims for, is this problem that it can solve by, the words would be, back substitution. When you've started with your original problem, got to this one, then you just have a back substitution, you go backwards, right? Oh, so much, I'll mention the Kalman filter. That's a similar process. going forward, that's called prediction. Going backward, that's called smoothing. And so Kalman had the great idea that he could break these problems that were fundamental in space computations into for prediction and smoothing. Okay, once again, we've got off. Yes?
Today you introduced the beam. There was a very good visual.
Oh, the beam. Okay.
Yeah.
Right.
So help me visualize what this was all about.
Let me help you even more before the question. I said it's better to draw the beam this way. I like the beam better this way, because the point of the beam problem is loads are acting, and we'll see this, of course, later. Loads are acting perpendicular to the direction of the beam. That's why the beam bends, so it'll bend a little, right? And that is what leads us to its bending moments and other stuff. If you haven't met beams, well, it'll be great to just have half a lecture about, or maybe a lecture about beams. That gives a fourth order equation that I'll write down again. Fourth derivative equal the load. Yeah. Now, ready.
Okay, so this is kind of the question I'm understanding why you always put the negative signs up there.
Yes.
So is this like some sort of if you were to draw like a free body diagram, you kind of come out with a negative sign somewhere?
Yeah, now here I don't have the negative sign.
Right.
Because once I've got second derivatives twice, so the second derivative is in some way negative. I'll complete that sentence in a second. Somehow the second derivative, which is the guy that has the 1 minus 2, 1, somehow that's a negative thing. But fourth derivative is second derivative of the second derivative. Yeah, do you want to tell me what the numbers would be? As long as we're wildly looking forward to fourth derivative, it helps. Do you want to guess what will a typical row of the matrix be in when I go to finite differences, fourth differences? Probably have never seen a fourth difference. You may not have seen second differences before. That was a big deal then to introduce second differences. Those 1 minus 2 1s. That was second differences. Fourth?
14641.
Yeah, 14641 with minus signs. 1 minus 4, 6, minus 4, and 1. In some way, I would get that by squaring this guy. Yeah. And so that would be a fourth difference. And, yep. And we would get, we'd have, what's the deal with boundary conditions? What are you figuring on beam problems for a fourth order equation and a matrix that's stretching out further? What's going to happen at the left-hand boundary? I guess my specific question is, how many boundary conditions do I now need? 4. And the typical is 2 at each end. That's the balanced way. That's the way that would make this matrix sort of symmetric. So I have maybe at this end I say it's held at 0, and maybe it's just sitting on a log there, right? That boundary condition I would call simply supported. That boundary condition says that u of 0 is 0, because it's sitting there, but the slope doesn't have to be 0. What does have to be 0 there? It's sort of the bending moment. There's nobody's here twisting it, right? So the other condition in that picture would be second derivative equals 0. Maybe my point is that now you see what I said before, that getting the boundary conditions into the problem is often the hardest part. because I have to replace u of 0 equals 0. That shouldn't be too hard to do, but I have to use this other condition. Somehow it's going to screw up the 1 minus 4, 6 minus 4, 1, and I'll have two rows. I'll have two boundary rows at the top, two boundary rows at the bottom. I don't want to go further today, but I think maybe just mentioning this gives you the picture of, sort of how things fit together. We would still have some nice constant diagonals in the middle, but now we'll have two boundary rows at each end. Yeah. So that's something to come. Right. That'll fit. Yes. Now, back to reality, which is any questions? Yeah, thanks.
You're saying for the lower diagonal, for the lower triangular.
Lower triangular guy, yeah.
You march forward to invert it. What do you mean by that?
What do I mean by marching forward? Okay. Yeah. So let's see. What would I? I'll replace this. Yeah. Let's see it better. I would replace this by maybe u. I'll use a different letter, n plus 1, at un plus 1 minus 2 un's plus un minus 1 is some right-hand side, if there's a force acting on my thing. So Fn, maybe. By marching forward, I just mean that this equation, that I can go in order. I can start with u0 and u1. They come from the boundary conditions. Then this equation will tell me u2. I use the equation with n is 1. This says u2, some u1s, some u0s, f1s, all that I know. In other words, once I get started, I'm on a roll. If I have two boundary conditions to get me started, then the equation tells me u2, and then the next time, u3 minus 2u2 plus u1, I can find u3. So I can get those, I can go forever. If you give me enough to start on, two things to start, then I march forward. Whereas in our problems, we've only got one thing to start on, and we've got one goal to hit. And that's why we have to solve the whole system together. This is we can solve it step by step. This is way faster, of course, to be able to just go forward in time. Yeah. So, I'll mention that the topic of initial value problems and finite differences for them, that we can't get to that. So we're seeing a little bit here, but it's done properly in 18086 in the second semester. Is the initial value problem part, and that has its own interesting questions. Yeah. Okay, so somehow we've talked about fourth order equations, initial value problems, but no homework problems. So I'm ready for, or even related, but that's fine with me. Maybe, so that, is there a question? Yeah, thanks. Or it doesn't have to be a homework question.
Yeah,
another question.
About the format of the homework. I wasn't
Yes.
sure, so basically, can I do everything in MATLAB and write down the answers?
Oh, good question. You mean I should just send the homework out to Natick, where MATLAB is? Do you know that MATLAB is just 15 miles away? I almost get there. I live 2/3 of the way there. Yeah, so we could just send the whole thing out there and get it back. That would save a lot of work. Not only, yeah, I suppose. Yeah, I suppose I'm okay. Why should I say no? Anything MATLAB can do and you can make it do, I'm okay with that. Yeah, I don't see that you have to do things by hand if you've got a better way. Yeah, yeah, that's okay. And then probably the answer gets printed and you can graph it. Yeah, so that's fine. So, I mean, somehow a course like this has got two parts to it. Or applied math has two parts to it. The modeling part, set up the equation, think, what is it you're supposed to do? And then step 2 is do it, the numerical part, the computing part. And that's where MATLAB, Python, Fortran, whatever, is going to do a lot of the heavy lifting. Yeah, yeah, yeah. Was there another question? Yeah. So that first homework was certainly very general intentionally, because I'm hoping you will read the book. You know, the lecture, you'll know where, you'll be able to match the lectures with the book even later on when they separate a little or separate more. You'll see what we're doing. And the homework problems, you should look at some of the others just to see, do I know how to do that? Right. Okay, let's stop here for this first review. I'm sure we'll have more questions will build up for the second week.